Okay, there's another example that we are going to have here. As you can see, a car weighing 130 kilonewton. As you can see, this is the car weighing 100. This is the weight of it, going to be 130 kilonewton when fully loaded. It is fully loaded, the maximum load inside, including the people inside it, is pulled slowly up a steep inclined track. So it is being pulled by a cable, as you can see here, upward, up a steep inclined track, as you can see, by a steel cable, as you can see here. The cable has an effective cross-sectional area of 490 millimeters squared. So this is the effective area of the cable. And the angle alpha of the incline is 30. So this alpha equals 30 degrees. Calculate the tensile stress sigma T in the cable, in this cable. Try to get the tensile stress because there is force being applied on it here, of course, that is pulling this car. Okay, so what is the idea here that we can go through in order, or what is the main configuration that should be understood for the free body diagram of this car and the pulling force? So we have an inclination, we have a load that is being applied from this car, which is W, for example. Here it is given 130 kilonewton. And of course, this weight, it has two components, one in this direction and one perpendicular to it. Okay, and here we have force that is being applied to pull the car, can call it like T, and we have the angle of the incline, which is alpha, it is 30. So simply we are going to get this pulling force, okay, that is going to be on the inclined direction of this incline, based on the equilibrium of the whole system. Okay, equilibrium of the whole system. We have a component of the weight in this direction, and we have this T, which is the pulling in this pulling force up this steep inclined track, making the equilibrium equation with summation of x in this direction equal to 0. We can obtain T, which is going to equal to the horizontal component of the weight, okay, times sine, for example, or this horizontal component of the weight at least, okay. And then from this we can obtain the force, and from this force we can get the stress in this cable, because we know already the area, which is going to be here 490 millimeters squared, and here we can put force, and then we can obtain the stress. It is a straightforward example. Let's have this calculation for us. A car on inclined track. This is the free body diagram of the car, as you can see. We have the weight of the car. It is in the vertical direction. We have, of course, some reactions, which is going to be at the wheel location of this system, but we are not going to be interested in it because we are interested in the direction or the inclined direction, not in the perpendicular direction to this incline. Okay, so always we are going to have our equation of equilibrium on this inclined track. So W is going to be the weight of the car. T, it is going to be the tensile force in cable, and alpha, it is the angle of incline. It is going to be alpha as given, and A, it is the effective area of the cable. Okay, R1 and R2, they are the wheel reactions. We're going to assume no friction force between wheels and rails. Okay, there is no friction force at all. So this no friction force means that there is no horizontal forces are going to be developed, so that we should take it into consideration. This is the meaning of no friction force between wheels and rails. Well, the first thing that we are going to do is putting the equilibrium equation in this inclined direction. So we are going to assume that the direction, the positive direction, is going to be upward, is going to be positive, and any force heading toward it is downward, it is going to be negative. And then we are going to say that summation of forces on this inclined direction should be 0, because this is an equilibrium. The system should be under equilibrium. Then we have T, which is going upward, it is positive, minus minus W sine alpha, which is going to be, as I said, if we say this is the weight, then it has one component here, one component perpendicular. This component is going to be W sine alpha, okay, the component of it, equal to 0. There is no other forces here that is being applied. So simply we can say that after rearrangement of this equation, we can say T equal to W sine alpha. We know W, we know sine alpha, then we can obtain T simply, right? So this means that the tensile stress in the cable, in this cable, is going to be, which is sigma T equal to T over A, or the area of the effective area of the cable, which equals to W sine alpha over A. Then we can substitute with the numerical values to make it or in the end, okay, of all the calculation. So W, it is 130 kilonewton, alpha 30 degrees, the area is 490 millimeters squared. Then stresses in the cable, or the stress in the cable, is going to be 130 kilonewton times sine 30 over 490 millimeter. It is going to give us 133 megapascal. This is the stress in this cable due to the this core. Okay, thank you, and see you in another video.